Assume that we have a sample of size 50 cereal boxes off of a manufacturing line. The target weight of these boxes is 16 ounces. The weights will pass inspection if they are within 0.4 ounces from the target. Assume the weights come from a normal distribution. You can find the data in a file called cereal box weights. The questions for this problem are on the next slide. Here are the questions we're going to answer. First, we will verify that the data does indeed come from a normal distribution. Then we will create a preliminary analysis with a numerical summary and see what we think. Then we check the probability of it failing on either side alone, then combine the two to get the overall probability of failure. Finally, make a recommendation in terms of the real world. Let's assess what we know. So what are the things we know from the problem? We know that the data comes from a normal distribution, at least we think it does. We also know that in order to pass, the cereal box weight must be between 15.6 ounces and 16.4 ounces. We have been given a sample of size n equal to 50 cereal boxes. So what do? Well, first, let's see if our normality assumption holds. We will do this by creating a normal probability plot of the data. Here's the normal probability plot. From the plot, we can see that the data does indeed hug the 45-degree line. We can also see that the p-value is greater than 0.05. So the normality assumption seems to hold. Now, normally we are given the parameters for the normal distribution. In this case, they are unknown. So now what? So in this case, since we are not given the parameter values but are given data, we will use the data to estimate them. This works nice and neat for the normal distribution because the parameters are just the mean and the variance. Here are the calculations for the mean and the variance. So now let's look at question 2. We found that the estimated mean is 16.245 ounces and the standard deviation is 0.2465 ounces. So we can see that the mean is roughly one standard deviation from the target on the high side. The fact that the mean is shifted toward the high side and the size of the standard deviation leads me to think that we may have a problem. Now let's look at question 3. So for this question, we'd like to find the probability that the next box weight will be larger than 16.4 ounces. Recall that this is a continuous distribution, so greater than and greater than or equal to are the same. This will tell us the chance of failing on the high side. Now let's find the z-score for x equals to 16.4. The equation and work to find the z-score is given in the slide. Our z-score is 0.51. Now let's use the CDF to determine the less than probability. From the z-table, you should find that the probability that corresponds to z equals to 0.51 is 0.695. Now we have everything that we need to answer the question. So since we have the less than probability and we want to get the greater than, we will subtract the less than from 1. The probability that the next box weight is larger than 16.4 ounces is 0.305. So we conclude that there is a 30.5% chance of the next box weight failing to the high side. Now what about the low side? So in this situation, we would like to see what the probability is that the next box weight is less than 15.6 ounces. Let's first look at the z-score. The equation in the work to get the z-score is given in the slide. We determined it to be z equal to negative 2.73. Now let's use the CDF to get the less than probability. By looking up z equal to negative 2.73 in the z-table, we see that the corresponding probability is 0.0032. Let's put this one together. Since we are looking for the less than value, it becomes what we found in the table. So the chance of failing based on the low end is 0.32%. So now what about the overall failure? We can get the overall failure probability by just summing the failure probabilities on both sides. So in this case, it becomes 0.3082. So at this point, we would conclude that the probability of making the next box outside the weight limit is too high. We should probably recommend trying to reduce the mean back toward the target, since it is usually easier to adjust the mean than reduce variability.